So here we're already getting some fits up, and for this little clicked pixel that's at the edge of, this is the Quabbin Reservoir in Massachusetts. It's actually where the city of Boston, where I live, all of our drinking water comes from out in the western part of the state. And so this is a very protected piece of land, and we do see fluctuations over the years, something a little more like the cyclic change in the different archetypal examples we looked at before. You'll see the two LandTrendr fits have already popped up. So the blue lines there are the actual connections between the composite values. And if I hover, you'll see a little dot, this 1,992, it's 1992. It's just a weird date formatting. But you can see kind of the points along this trajectory of the blue line are the same thing as the points that were in they were shown as like black points in the input time series in the figures we are looking at. And you'll see for the two different bands, we've seemed to get a similar break. This looks like it's broken in both 1992. We've got two distinct segments, those red lines there. And as with the other tool, you can also pop out the chart and look at it larger if that's helpful. Now, would I say that's a really good fit to this time series? Maybe not. There's a lot of noise in there, and we could do a lot of tweaking to try and get a better trajectory, but this is a pretty noisy time series. We can see when we switch to the CCDC view, first thing to note, CCDC takes a lot longer to run than LandTrendr. It's the difference between compositing a bunch of values to get annual time steps versus taking all of the observations and iteratively fitting harmonics and looking for change. So you got to be patient when you're waiting for CCDC results, and this might factor into considerations on working with the algorithms. CCDC is much harder to run over large areas. It takes a lot of memory and the result storage, a little more complex with the more coefficients. But here you can see CCDC's found quite a few segments. We've got 1, 2, 3, 4, 5 segments, and then this whole period that we actually didn't get a model fit. And that also happens with CCDC sometimes. If the time series is too noisy and it can't find a stable signal, it won't fit. And that can be problematic for mapping purposes. If you wanted to flip this back into the spatial domain, we would just call that disturbed. It's kind of a no classification, no data period, because we don't actually have a model we can classify the segment for there. And let me just pop that chart out again so you can get a little clearer view. So that same time series, see, it's edge of a water body, lots of noise. Maybe this is not the best technique for fitting this, but the tool, you can go in and change the parameters, you can adjust. So let's say, for example, I might make my recovery threshold for LandTrendr a little higher and click this pixel again. And let's see, should give it a second there. Didn't change results too much, so not really sensitive to that. I could also do things like, say, maybe instead of compositing over just a single couple of months there, we could do it over a whole year. So lots of ways to kind of get in there and try and experiment with some different parameters. I don't want to spend, okay, there we go. So look, if we did annual composites, now we're getting a more complicated trajectory that maybe is a better representation of this time series. You're also seeing that for the NBR fit, we're getting an extra vertex in 2003 that we don't seem to get as clearly in the Tesla cap wetness fit. So this tool is really great for experimenting with all of the different parameters. There's, again, quite a few in there, so we want to make sure that, you know, before you go and run this at the landscape scale, that you're going to spend some time trying to tune in exactly what works best for your study area. So I'm going to invite everyone, let's put 10 minutes on the clock this time and make it a little bit shorter because we do have a lot more to get through. But just like we did before, click around, visit that same site that you were looking at patterns in before, places you know well, look at the different results, try different bands with LandTrendr, try those different compositing dates, adjust some of the CCDC parameters, especially that min observations, and see if you can get some trajectories that represent what you think the kind of path or the kind of shape of that segment or temporal set of segments and breaks should look like. And for those, keeping a doc or a Jamboard, if you're visiting the same sites, another good place to put some notes in there. And I'm going to be monitoring the chat as well. And this would be a good time to ask if you have any questions about the algorithms. We can get back into some of that too.
Valerie, the two of them use Landsat. This is
yes. I should mention this app is using all the Landsat observations. I'm not sure that we added Landsat 9 in, but it's using 5, 7, and 8. By default, it's all built on top of kind of the standard usage for LandTrendr. I'll share in the next slide some of the API tools that Justin Broughton has developed. So we kind of took pieces out of that and some standard CCDC tools that Paulo had developed. But yes, all Landsat based for the app, but you could run this on any time series with the algorithms, either in their native implementations or in Earth Engine.
Okay, perfect. Thank you.
And there's a question.
Yeah, there's a question in the chat.
Yeah, about updating. So for this app to update, you just click the pixel again. So you'll see the little black square pops up on the map where you clicked. And if you change the parameters, you can click that same square again, and you should get that same time series back, but with the new parameters applied. Your segmentation results are very dependent on how clean your signal is. So for LandTrendr, what we're trying to do is get the most comparable observation out of every year. And since we're taking a median, we've got a little bit of extra flexibility, right? If I've got a really bright observation in the summertime and we didn't cloud mask it, when we take a median, we're gonna go more towards a central tendency, but we're hoping to get a nice, clean, every year, most comparable observations. CCDC handles noise in a bit of a different way. Because we've got all of the data, we don't kind of smooth out the individual observations like we do in LandTrendr by taking a composite. Instead, we use a lasso regression. So we shrink the coefficients so that we're not as responsive to the noise. And that is the lambda parameter in the CCDC fit. So if you know you've got a noisy time series, you may want to increase your lambda. If you want a really close fit to the data, you feel like you've got a really clean signal, or you want to fit some nuanced signal there, you may want to try and decrease the lambda. So both algorithms handle noise in different ways. They both have built-in, like, parts of their construction are directly addressing trying to get us the cleanest signal possible, but there are some knobs you can turn to address specific use cases, or or make yourself, be less responsive to noise if you know you've got noisy data. And I also would suggest the paper that I linked to earlier. I'll see if I can put the link back in the chat again. There's a bunch of, like, I tried to collect all of the references. There's a pretty thorough literature review of use cases. So both the original algorithm papers and a lot of applications should be a great starting point if you're looking to understand more of the nuance, both in terms of the mechanics. I would go to the original publications for that, or how people do this in practice. Last thing I'll say, a lot of folks more recently have come to ensembling things. So you'll see more papers where people are combining multiple LandTrendr runs, or runs fits from LandTrendr and CCDC to be even more robust to noise. So there's lots of ways to try and overcome that. There's also a question about adding the normalized difference chlorophyll index. That's a great question. I am learning so much more about oceans and water bodies than chlorophyll as I could present more of these tools. We could definitely look into it. I will make a note of that. And as I mentioned before as well, all of the like the algorithms are all available in Earth Engine. So if you're an Earth Engine user, you could get into the LandTrendr code fairly easily and make some modifications. CCDC is a little more challenging in terms of the tools. A lot of times we deal with like pre-run data layers, and I'll show you a tool that accesses some of those. But you could definitely add it yourself, and I can kind of circle back with Paulo, who helped build this one, and see if there might be an option to add it in to the app that you're playing with now. All right, I know it was just a brief amount of time. Hopefully if people are interested to keep exploring things after the sessions, but maybe we could take a minute. Any impressions, things that you couldn't get to fit well, things you expected to fit well and did not? Any comments? Feel free to either put them in the chat, or folks online can unmute. I'm not sure what in the room if we've got hands or microphones.
We have a shy lady here. We are pushing her to share.
Yeah, it's all exploration, and I always learn something when someone else shares their examples. Like, you never know what you're going to see until someone starts looking at their own study areas, own data sets. Yes, there's a good comment.
Yeah.
Yeah, it is certainly not a magic box. There's a lot of iteration, and that is what the creators of both algorithms recommend. When you're first getting started, why we have tools like this is that you can spend some time tuning parameters. It makes a lot more sense to click a few pixels if you've got reference data, if you've got plots, if you're doing field work. Go and try and get those parameters right before you start running a bigger footprint, and run a little footprint if you're scaling out before you run a whole state or a whole country. So iterating is definitely a part of the process here, both of these algorithms. Much like, again, I keep coming back to object-based analysis and like semantic segmentation, that often takes iteration as well. If you've ever worked with a program like eCognition or any other spatial grouping of pixels, it's imperfect, and you gotta iterate on it.
Yeah,
but
they are unsupervised methods, and that's the trick. No, you have to try a lot.
Yes, for sure. And that's a good point, like thinking about supervised versus unsupervised. You might imagine a world where you could train on some corpus of shapes, but that would be really tricky given the complexity of signals. So unsupervised is definitely an advantage here, but it comes with that parameter tuning stage. So I think do we have a comment, or? In the interest of time, I might just move on to just a couple more points on this before we go to the next section. So these links are in these slides. I can post the link to the slide deck again, or if someone who has it before could paste that again in the chat. But Paulo, who built the tool that you were working with, has a whole other tool, looks very similar. You'll see the panel to the left has a lot of the same parameters, but also includes more options on charting. You can access existing CCDC runs. So there is an effort to run CCDC globally as part of a bigger land cover mapping project. So you can access some of their shared data layers, I believe, and generate synthetic images. So I was talking about predicting images along these curves. And so he's got another whole tool as well as a documentation page. So here, like, you can read all about the different use cases and experiments. So if you're interested in looking more at CCDC, and uh-oh, I have trouble getting back to my original tab here. So sorry about that. Let me switch back to this. And similarly for LandTrendr, I'm not going to risk bumping out to that other page, but Justin Broughton, who works closely with Robert Kennedy, who developed LandTrendr, has a whole bunch of apps. So the one I'm showing here, again, similar parameters, you know, your date ranges, start year, end year, and there's a bunch more of the parameters if you scroll down. But here you can actually make change maps. If you saw, LandTrendr runs much faster, so it is really feasible to generate a segmentation result and look at it spatially. So here I think we're looking at the time of most recent change would be my guess. But at their page, eMapper, GitHub.io, LTGEE, these links are again all in the presentation, but they have all sorts of documentations on both the LandTrendr functions and a whole bunch of different tools, including one that's very much like what you're seeing in the tool you were using. So if you want to keep kind of digging into either one of the algorithms, these are all great options. The tool we were using was designed mostly to compare both algorithms for the exact same time series. So if you're looking to decide between them. And I think with that, again, we're gonna keep moving along here. The next approach I'm going to share with you. So we started by just thinking about time series, no fitting of anything. LandTrendr and CCDC are these unsupervised temporal segmentation algorithms where we want to divide things into, we want to put like with like, similar segments, and then look for differences between them as a way of detecting change. This approach is something that I worked on after many years of working with CCDC, and really I wanted to be able to make use of the harmonic fits and all of the data, but perhaps be a little less prescriptive. So there was a question earlier about, can you define the length of the time series that you're fitting? And CCDC is determining that for you. But I wanted to work on an approach where you had a little more flexibility and was less about kind of classifying and finding segments and more about anomaly detection. And so I like to show these examples. So these are tasseled cap greenness and wetness time series for a bunch of different types of forests. As I said earlier, work mostly in temperate forested ecosystems where we have a really strong phenological curve. And so you could imagine if you take 30 years of Landsat data, which is what we're looking at here, the colors are the different years and you kind of stack them all up on top of each other. So we're looking at the day of the year versus the greenness signal or the wetness signal. You start to see these really clear shapes. And just like CCDC wants to compare new observations to a fitted model to detect a change. And I said so many in a row, and we say, okay, if I've got 5 anomalous values in a row, that's probably a land cover change. What if we just think about, is it a change? And a lot of this work evolved from thinking about gypsy moth, now known as Lomantria dispar, or the spongy moth. It's been renamed, but we had this massive insect defoliator outbreak up in the northeastern United States. Not as familiar with defoliators down in South America, but here the Lomantria dispar caterpillars will eat all of the leaves off of deciduous trees, especially species of oak. And so you get a forest where suddenly it's not green over the summer, but it is still a forest and those leaves come back. So we wanted an approach that was somewhere between this temporal segmentation where we say, this is a forest and now it's built, or, you know, this is water and now it's barren or dried up lake bed. And we could say, oh, this season was anomalous. And so with that idea of, can you fix a segment length, worked through an approach where you fit a baseline. So assume there's that cyclic pattern, and you define how long it is. I typically use a 5-year baseline with Landsat data. It gives you a good trade-off between the number of years included and the number of observations that we have. And you can then compare observations during what I call monitoring period to what would be expected from this baseline model. And you could think, if you were to fit a whole bunch of these kind of moving window approach going back in time, time, you can then say, well, maybe the year before the monitoring period had some bad data. We talked a bit about noisy observations and cleaning your time series. So, okay, maybe I've got some bad data in there. It's Landsat 7, I've got scan lines. Maybe the years before are actually a better representation of this system. So using the power of lots of short models instead of trying to fit one very long model, we can start to make a lot of comparisons. And so here's what this looks like in practice. So you can imagine you've got this big long Landsat time series and the colors represent different 5-year periods. You can imagine there's lots of these little baselines that you can start to use for monitoring. And essentially what we do is for each of those squiggly lines, those harmonic baselines, we make a prediction for each observed value. So here the white values in this kind of cartoony version would be, I actually observed this Landsat value. And we could do this in NDVI, we could use this in tasseled cap greenness, you could pick your index here. Usually vegetation sensitive indices tend to work best, but you can then take the real value and compare it to predictions from these different curve fits and start to build up a prediction of how anomalous was this value relative to the baseline, and get not only an estimate of the deviation, but you can get a mean and a variance around that. So we essentially take each observed value, subtract the predicted, divide it by the root mean square error, pretty much a z-score here, and we now have an anomaly. And if we do this for a bunch of different images, just some schematics here, you can get this normalized anomaly or condition score in the form of images. And if you start to do that across a whole bunch of different dates, again, you can get a mean and a variance. You do this for different orbital paths, and suddenly you've got a continuous map of not segments and breaks like we had from CCDC and LandTrendr, but anomalies. And here's what this looks like. Sometimes we apply a smoothing kernel, it makes it look a little more like polygons, but in these maps, things that are more red are less green. So in the given time period, they were more than 1.5 times the model uncertainty, the RMSE, away from the expectation from this set of baseline models. And the kind of bluer tones are actually more green than expected. And this proved really effective for looking for defoliation outbreaks, and I'll show you some other types of land cover change as well. We won't play with this app as much. I've worked on this a lot in the northeastern US. It is not scaled globally, so the maps that I have are all for kind of those northeastern US states. The link is in here though, and you're welcome to go and click around. What we're looking at here is a time series of these anomalies. And when this little slider gets to 2016 and a click or two, here we go. We're going to see a big spot light up in the state of Rhode Island, kind of spreads out in 2017 and disappears in 2018. That is that defoliation event. And this is a more flexible approach to specifically looking for condition changes in greenness, following some of that harmonic logic of CCDC, but without trying to build in the full iterative change detection procedure. And yeah, so here's those outbreaks events. And if we zoom in a bit, just to show you what this looks like for a single point, here, this tool gives you a clicked chart, and you actually get a time series of the anomalies. You can see a really big deviation, that really negative value, much lower than the expected greenness in 2016 when that forest was defoliated. But you can also see that it recovers in 2020, most of these affected areas. We did see a lot of oak mortality, but things did green back up, whether it was the original oak trees or new things coming in. And again, just going to move through this pretty quickly, but another example of change detection, and doesn't just work for forests. As you go through these maps. We found lots of changes. Here's an example where we had a housing development go in. So this much larger anomaly, this built area comes in, and then over time actually starts to look greener, because you can imagine as those fits move forward, we're now measuring our current greenness relative to what that period when the development first went in, and you almost get a normalizing effect. And I guess the last example in here, we also had a tornado in the state of Massachusetts where I work, and just a final case where you can see the tornado path. There we go. So that big red and orange streak is the tornado. In this case, we then saw a lot of vegetation recovery. So just an example of, in the suite of ways that one could approach time series analysis and change detection, this is geared towards detecting anomalies. I should also mention there's been a lot of work by the US Forest Service and lots of other groups where you can use not necessarily harmonics, but you could use a composite, sort of like what LandTrendr does, look at the max NDVI for the previous 3 years and do a z-score approach to say, is this year anomalously different? So kind of a more generic way of getting at changes in greenness. And I can stop there for a second. Anyone has questions before we move along? Again, mostly just another use case of harmonic modeling, but in generic change detection. And so all of the approaches that we've looked at so far have been, I said way back on that objective slide, space first versus time first. So in everything we've looked at thus far, it's been time first. We take a single pixel and we've drilled back through all the observations that we have for that one pixel square, that one location. And we're making judgments about the history based on just the pixel, as if it doesn't have neighbors or other spatial context in there. There are ways that one could think about building some spatial context into temporal segmentation. For example, you could add a time series of texture measures. So you could run some sort of kernel-based GLCM or other kind of texture computations, and then use that as a feature when you're performing your segmentation. But an interesting take on this would be the dynamic world data set. So I'm not sure if folks are familiar. It was just released earlier this year, although Google's been talking about it for quite a while. But dynamic world is a near real-time land cover classification. So this is an example of what I would call a space-first approach. Rather than trying to take the raw reflectance values or spectral indices and then generate segments that we can label, first we take an image and we assign labels, and then we can track that through time. So I won't get too much into the modeling detail. Happy to try and answer some questions about that if folks have them, but Dynamic World uses a deep learning approach. It's a FCNN where we've got a lot of supervised annotated data plus some unsupervised information coming from the actual Sentinel-2 imagery that's used to create single image predictions of class probabilities. It is available in Earth Engine. This is the recommended, if not the only way to work with dynamic world, because a dynamic world classification image is generated for every Sentinel-2 L1C image with less than 35% cloud cover. So it's a really big data set, but it's again, a different way of thinking about time series. So here's an example to illustrate what I mean by single image predictions. This is that same reservoir that I was clicking some pixels in earlier. And if we look at these images, this is February through June right here, the source image in the top row and the classification images in the bottom row, you can see it's responding to ice conditions. So we've got frozen water back in February, which is winter up here, and greener forests in June. If we keep moving through the year here, you can see again, we're getting the land cover predictions are responding not to kind of a harmonized segment like we had in the temporal segmentation algorithms, but you're actually getting for that date what is the best guess at these different land cover classes. And much like the way we could take time series of reflectance and look for signals, with dynamic world, you can look at time series of the class expectations. So this same set of images, if the white point here is our clicked pixel, and I bet you can foreshadow there's a tool coming soon, but we can see this is a snow ice probability for the reservoir. So kind of in the colder months, we have a high probability that this land cover is likely snow and ice with a little bit of probability of bare. And then as the weather warms, this flips to a more definitive prediction of water. And you could then start to do things like, I mean, you could fit a temporal segmentation to this if you wanted. You can take composites. So a common way to work with dynamic world is to take a most frequent, a mode label. So you say which class is the highest probability and does it occur, how frequently does it occur in the time series to get a map. And you can get something that looks like this. So if we take the mode of the most common class for each image over a year for that area, you get something that looks very much like a standard land cover map. And the interesting shading effect that's kind of coming in and out there is if we apply a hill shade, so a model that's usually used for terrain visualization, but if we apply it to the class probability, so we say, okay, for this pixel, what is the probability, the likelihood of it being the class that's shown by the color. So if it's green and predicted as forest, the places that get shown as shaded more darkly here are places that have actually a lower probability of forest than some of the surrounding pixels. And in this case, if you look in the inset image, we've got this big power line corridor cutting across the linear feature or the lakeshore edges. We get a lower probability, so the model was less certain on aggregate of the labels there. And depending on which dates you pick to make your composite, just like with LandTrendr, how it was very sensitive to which period you picked to choose a reflectance value, you can get some really different maps. So if we look at kind of a wintertime cold season map for this area, we're getting a lot of snow and ice classification. Even in the forested areas, most of that is places where you're seeing forest through the trees, kind of on the canopy floor. And when you go into the warmer months, you tend to get a smoother picture. Everything's a little more stable when we've got leaf on conditions. If you take the whole year, you get a little bit more noise, greater uncertainty. So again, the idea of working with classification model best guesses as opposed to reflectance values. And if we think about this in that kind of time series sense, we've been looking at all of these other tools that you get a visualization of the time series. Here's an example from Oregon in the Western US, and you can see this pixel if you're looking at the single date predictions kind of flashing through on the right, and the little time series chart up there in the corner. This was a forest. The model was very certain. We've got a high probability of forest for the first part of this time series. And then sometime in late 2020, this was cleared and suddenly our class probabilities are a lot noisier. We're getting higher probabilities mostly of shrub and scrub, a little bit of grass. So we've got a change in cover. And now imagining those temporal segmentation algorithms, again, you could imagine fitting something like that to the class probabilities instead of reflectance values. So one more tool for you here. I think we're doing okay on time. So this is the same tool that I was just showing the screenshots from. So and it'll take you right to the same place if you want to explore there. Here we can adjust the composite date. So the date over which we're getting the, in this case, the mode probability. And this also affects what we get the time series view of. So to show what I mean by that, I'll click a pixel here. So we're getting a time series from January 2021 to the end of 2021, so January 1st, 2022. If I were to move this date back, we have this for a big chunk of the Sentinel record. Like I said, all images with less than 35% cloud cover. Now that same pixel, I'm seeing the time series chart for a longer time range, and we're getting the corresponding average of the classes or mode of the classes here. And much like the first tool that we explored, if you click the pixels in this time series, we can then get the individual, not just the prediction, so what the model was guessing this would be, but also the underlying image that was used to generate that prediction. So if we let this load, so here's my Sentinel-2 image, and here's the corresponding land cover classification. And we could say something like, oh, something looks a little weird in the time series here. Well, we've got this big snow and ice now over all of the landscape. And if I look at that Sentinel-2 image, you can see it's doing a pretty good job picking up on where things are higher likelihood of being mostly snow and ice. You'll also see holes. These are places that clouds and cloud shadows have been masked. It's one of the limitations of this. I think I mentioned earlier, cloud and shadow masking for Sentinel-2 is an ongoing challenge. So we kind of are overzealous a bit in some of the masking, but it's really, like I said, a new way of thinking about land cover mapping, where we're getting these near real-time predictions of cover that we can use to do change detection with. And so I'll get to questions in the chat in just a second. I want to switch back to my sorry, this was working much smoother before. Back to the right tab here. And before I do that, let me put this link in the chat. And I think we'll spend about 10 minutes of our time left looking at these class probabilities in the time series, and I can answer questions in the chat. And while you're exploring, definitely try some different periods. Again, adjusting how the period will extend or shorten the length of the time series that you're going to see in that little time series pop up. Think about, you've seen some other approaches now. You've seen different types of change in the landscapes you've been looking at. How is dynamic world doing? What are some limitations? And again, adding some screenshots to your doc. So dynamic world, the legend is predetermined. So this was a collaborative effort between Google, the World Resources Institute, and National Geographic. They came together, came up with a taxonomy, their legend, and that is the classes that are applied at scale. So that collection, the classes you're seeing there, that is what it is. But I should say, one of the interesting things that has been experimented with in working with the class probabilities is that they are, just like you could perform change detection on them, they're a feature space unto themselves. So you can go in with your own training data and retrain a classifier, not on reflectance values, but on the dynamic world class probabilities. And there was a great example by Zander Venter, who's a Earth Engine user. He posted on Twitter, he had used the world cover data set and, sorry, not world cover, he had used the Lucas data set and had trained a classifier using Lucas points and dynamic world as the feature vectors and was able to improve the classifications, add more detail to the dynamic world legend. So again, anything that you use images for, you could start to think about the dynamic world probabilities as an alternate thing to experiment with instead of, say, NDVI or surface reflectance. But to get back to the question, the classes are already in there. What you see is what you get in terms of just the raw data. I will also say, so the images themselves have the class probabilities for each band as well as a label band, which gives you the highest probability class for that date. And that's the band you can use to make a mode composite fairly easily. If there's questions about how to do that, I can point to some tutorials. Okay, so last little bit here, a little bit more dynamic world. And again, I think this connects nicely to the question about the built or example of built. So I mentioned the kind of standard land cover visual you're seeing loop through the flat, just highest probability class. That looks most like what we're used to seeing in a land cover map. We can do that neat hill shade effect where we say, oh, let's shade it by the probability of that top one or most likely class. But a thing that we realized after the release of the product and hearing from folks like, oh, I don't see 10-meter detail. Is it really a 10-meter product? If we take the classes, so we've got 8 dynamic world classes, and we actually weight the colors in the image palette. So give this a second to soak in, but we take the actual class probabilities and we apply them as weights to the different colors we use in the legend. We'll see something like this kind of blurrier image that comes up in the GIF. And what that blending does is now, instead of just seeing the highest probability class and the uncertainty associated with that, I can start to see where things were predicted as mixtures. And so this is an example in kind of urbanized New Jersey in the US, where you've got a lot of highways. And in the simple most likely class, you're not getting that road detail at all. And you would say, well, where are the roads? Is it able to capture these urban features? But when you look at the multi-class kind of view, you start to see those roads show up in more orangey tones. And that's because they may be highest probability of trees at the pixel level, but that highest probability could be 51%, and it could be 40% likelihood of, in this case, it's predicting it as a kind of shrubby mix, which again, might not be correct, but that detail is in there. This also helps reveal things like street trees, and the edges of the built blobs start to get a little wider spread, as you can see some of the lower density urban areas. So this visualization, I think, really helps show what information is in there in the dynamic world features and why things like secondary classification, using it as its own feature space, works fairly well. So I'm not sure we want to spend too much time on this. If you are an Earth Engine user, this is the one thing that is not an existing app. This is a proper Earth Engine script. So the code is in here. This is using those class probabilities to make the blended image if you want to get into the math of how it was done. But here we can actually see, if I zoom out, that's going to give me just the flat view. But if I zoom in on this dynamic world composite with the blending applied, once we get zoomed in a little further, again, you'll start to see, things like the edges of fields are kind of slightly greener where there's some trees mixed in there, and we can see the river patterns a little better. And let me turn the top label on. So Yeah, you can see the difference in the information that you can visualize. So let me put the link to this script in the chat. If you've got an Earth Engine account, you're welcome to try it out. Again, if you don't have yourself set up on Earth Engine yet, these are all in the slides and you can go and try it later. And we have about 20 minutes left. I think we'll probably stop with enough time for questions, but if folks want to just spend a few minutes here playing with that script, looking around, any last questions on Dynamic World formulating in the meanwhile, switch back over here. This says 10 minutes, but I think we could probably take a little less if we've got questions. So feel free to put questions in the chat if you're able to access that script with an Earth Engine account. If not, if your neighbor is able to, you might want to share. But again, another way of exploring Dynamic World, and we can look through that, and I'll answer any questions if there's questions in the chat or in the room.
Alva is asking, how is the blending visualization made?
Yeah, so it's all in the code. I'll admit, Chris Brown, who did the, who wrote the paper and built the model, came up with this visualization. It is a linear combination of the probabilities applied to weights to the palette colors. So if we take each of the colors that you see in the legend, so we have say the green associated with forest or the red associated with built, and we actually take the RGB value and then we weight the contributions of the red, green, and blue there by the class probability and then sum them up, because all the class probabilities are on 0 to 1. So we can kind of weight the contributions of the different colors. We get this blended visual. I think he added a scaling parameter in there that kind of brightens it up a little bit. The code is out there. It was also posted on Twitter and a couple other places. So feel free to dig in and look at how that's done. But I mostly showcase it as an example of, again, that finer scale detail that doesn't seem so obvious if you're just working with the standard winner takes all, most likely label.
She says thank you.
Excellent. Yeah, it's a cool idea.
Really cool visualization, and it provides like important information, I believe. It's nice.
Yeah, it's like, just like we were looking at the RGB images, it's almost like, right, we get like blending of the different colors for different spectral bands. How do you think about that in a class and class probability sense? And yes, Diego's commenting, the sand looks like snow. It does. That is the biggest source of confusion in Dynamic World. Bright things often get labeled as snow and ice. So salt flats are a big limitation. We see a lot of cases you get those, the really bright surfaces get mislabeled. And I think that's a place that like future improvements definitely need to be made, like very obvious misclassification as sand or salt as snow. Question about the time machine on the apps platform. I'm not sure if I have it shared in the public apps gallery. That's a note for me. I've only recently been developing it, so I've been kind of staging the releases. I'm eventually hoping to have a Medium post that talks more about some of the sensors and that sort of thing. But the link is in the presentation slides, and I can put it in the chat again. And I will check this afternoon. If it's not public, we can make it public, or my contact information will be in a couple slides, and folks are welcome to reach out if they lose track of any of these materials and need the links again. And we have a Slido in here. Maybe we could pull out the phones again. I understand if people are kind of winding down in this session, but out of curiosity, I guess, just for my own having developed these things, did you prefer being able to look at the time series, or did you prefer to look at the kind of blended visualization there? Or sorry, I think it was the top one, the hillshade, or the blended. I have a feeling this is a little bit of a loaded question, but I think if we click, there we go. Sorry, I said the wrong choices. Oh, I got some votes for the health shade. Nice. Yeah, that top one label is going to be more like what you're used to seeing in land cover maps. And I think that's kind of the transition we're going to see in the coming years, is shifting from every pixel gets one label to this more blended, mixed probability landscapes. And as you start working with these continuous values, I think we'll also see more and more of these creative ways to try and flatten all of that higher dimensional probability information into a single visualizable layer. All right, so in our last 10 minutes, I figured just a few summary points here. So kind of the recap pictorially on the right there, but we started with some exploratory analysis, always the best place to begin. You want to look at your time series if you're going to be analyzing a particular process or place, understand what's in the data, how long a time series do you need, what spatial resolution do you want, do you need specific spectral bands, thinking Sentinel-2 with red edge. Maybe you're doing something that's really important, which would make it like less suitable for a Landsat based analysis. Or if you want to look at a really long time series, you're interested in change on decadal scales. Landsat's really one of the only sensors that's going to give you that at a moderate resolution. If you need high frequency data and maybe resolution isn't as important, or some of the ocean monitoring problems, MODIS ends up being really useful. So being able to look at those examples, think about what you're trying to characterize. When you're doing temporal segmentation, that's that time first approach. We want to look at trajectories or define things in segments and breaks. And I want to keep coming back to, it's just like spatial segmentation or semantic segmentation, object-based analysis, except instead of an image, we flipped from the spatial domain into time. We want to group things. We want to find the edges between things. We want to label things that are similar, but temporally as opposed to spatially. If you're looking at just anomalies, you're less interested in having these defined segments. You simply want to say, does this observation look different than it did in the past? Things like the moving window harmonic approach and the defoliation example that I shared. That can be in those lines, and there's lots of papers out there on anomaly detection and kind of shorter term condition monitoring as opposed to change detection. And then finally, where we ended, what if instead of going time first, we go space first? And now we're looking at a series of classifications, one per image, and using that to track change through time. So hopefully all of these tools are things that you can use to keep exploring on your own. Again, there's the slide deck link at the end. Here's a master list of all of the different apps that we experimented today, and there's plenty more out there. I encourage you to go look in the public apps gallery on Earth Engine, or some of the resources I shared on the individual algorithms. My email address is down at the bottom. I'm vpasquarella@fas.harvard.edu. If you've got questions, if you lost track of anything, jot that down. Feel free to send me an email. And with that, that is all I had for today. And I hope—
Thank you, Valerie.
Yeah.
Big applause.
All right. Well, I hope you all have a good rest of your week, and it sounds like you got a lot more exciting sessions along the way.
There was a question that I don't want to miss from Diego from just a minute ago. He's asking for tips for us that we are starting with Google Earth Engine. And he asked, how long do you think it takes to reach a sufficient learning curve and maybe to develop our own app?
Depends on how complicated an app you'd like to develop. So I mentioned, like, for a paper, if you get to the point where you know how to ingest your own asset, which is just a few clicks in the Earth Engine GUI. So I've got a raster map that I made. You could process it wherever you want, you know, R, MATLAB, Python. I made a data set. I added into Earth Engine in my own account. You could make a simple app that just shows that layer with a few simple buttons that you could probably master in I don't know, a couple hours if you sat down and tried to work through end to end. Something like the ones that I shared are definitely a much more laborious process. You've got to get yourself more familiar with all sorts of actions and commands on click and responses and that sort of thing. It comes with practice. Apps are also interesting because it's always a very customized thing in my experience. I would say, and I'm trying to find this quickly, but there's been a whole bunch of tutorials on apps at the Geo for Good Summit, as well as on some of the outreach events. I'm not finding this super quickly, but I know there was one recently where they walked through kind of a template for app building. So definitely check out the Earth Engine developers resources. And I think the last thing I'll show really quickly, because I know we're pretty much at time. If you are in Earth Engine, you may be familiar with all the scripts if you're an owner, reader, writer. But this last section, which is usually collapsed like this, of examples, this has some super useful starting points. And there's a whole section, you can see I already have it expanded here, on user interfaces. So if you want to see kind of how apps work or try and pull them apart and use pieces for your own, for example, here's a linked map script. And here you go. This is, linking a bunch of different band combinations for the same image, and you can actually access the code in here. And the deploying of apps is just a simple click up in the corner. You can create a new app with literally just a few clicks of a button. So apps can be as simple or as complicated as you want. And I'd say given a couple hours to, some of mine are still works in progress, definitely something.
You definitely use JavaScript, no?
Yes, you use Earth Engine JavaScript. I will say that too, Earth Engine builds in all of the widgets and things you use to build apps. I am not a JavaScript developer. All the JavaScript that I have learned has been through the lens of Earth Engine, but they do make it really easy, and there's great resources and documentation